The greater San Francisco Bay is a $400 billion economy. If it were a nation, it would be the world's 26th largest economy. Technology is dominant in this mega-region economy. HP, Agilent, Google, Intel, Apple, Cisco, JDSU, Chevron, Genentech, BioMarin, Biorad, Medtronic, Trivascular. These names are synonymous with computing, electronics, communications, optics, energy, biotech, and medical devices. The North Bay, Sonoma, Napa, Marin, and Solano, connected along California's famed 101, are not only a world-renowned tourism, artisan agriculture, and wine-growing region, we are also home to more than 300 manufacturers, and perhaps as many as another 400 to 500 smaller 1, 2, and 3-man shops who supply them. With combined output of more than $6 billion, these 300 companies are the engines of our prosperity. Their 20,000 employees are the promise of good jobs and rewarding careers, and their futures are inextricably linked with our quality of living. Think for a minute about products as different as the Boeing jet that brought you to your last destination, a NASA satellite, surgical instruments, or the Apple iPhone in your pocket. Each of these products contain parts or assemblies that are manufactured here in the North Bay. So these are their stories, and the story of our future.
I watch what's going on overseas, and everybody had said that manufacturing right now is doing very poorly because it's all being shipped overseas. And they said, oh, well, that's no problem because we're only shipping the rudimentary stuff over there. We're only sending a few easy parts that don't take a lot of precision. Well, the problem with that theory is, well, you send that over there, that's where everybody that is a machinist cut their teeth, was making parts out of, usually in some job shop somewhere, making easy parts. And that's when you learn to machine. Well, then as you grow and you get educated, usually in school of hard knocks, you then have the skills to make precision parts. So I was watching the news the other day. Here in the U.S., we still have all these R&D jobs. Well, they named several large companies that have now moved their R&D facilities overseas along with their manufacturing.
If you need to do what the Agilent instruments do, go to 20 or 30 gigahertz or 60 or 70 or pushing 100 gigahertz, you need a starting material for your semiconductor where the electrons can move quicker. And what we do is a trick, it's called compound semiconductor. And we pick elements from column 3, like gallium, and elements from column 5, like arsenic, and we put those together into one compound.
Remember we talked about we only do things no one else in the world can do, right? So intellectual property, the knowledge that we have, we want to keep it, right? That's one reason. Think about the automation, right? How much would it cost to buy all this equipment anywhere in the world? Same price, right? So the equipment's the same. So if you can automate a lot, right, you can do things here in the U.S. And one of the basic reasons we do this is time to market. If we can get our instrument out first before our competitors, and the customer really needs it, they're going to buy it, right? So if you can get out faster, if you can get out 6 months or a year faster than the competitor, you've got a huge advantage.
The industry standard for a centrifuge for separating blood is 12,000 RPM or 12,000 G, and our standard is 20. So we try to make the best tubes on the market. That's how we compete in Petaluma, being in business. Our tubes spin a whole lot faster than the industry standard. The reason parts don't centrifuge is you get core shift and you get a thick wall on one side and a thin wall on the other, and the thin wall blows out. And to spin at 20,000, you have to have perfect wall thickness on both sides. And then people ask, how do you get it so clear? It looks like it's polypropylene, but it almost looks like polystyrene. You do it by making the walls really thin, so you're not looking through this cloudy material.
One gets the sense in the educational system today that, we have sort of this one-size-fits-all. Every kid is going to take this math, every kid is going to take this science, and finishing high school, then there's 4 years of college, and then I have a degreed technical person. Is that the reality, or do you see maybe the potential for multiple paths, multiple career paths?
I'm really prejudiced, frankly, that we get a lot of engineers. We have a lot of engineers that we interview that were trained to be managers, and they're book smart, but they've never touched metal in their lives. And the guys that are really valuable to us are practically trained guys that like touching metal, like touching plastic, like running machines themselves. They go to college, they find out, well, if I'm an engineer, I make a lot more money. But even, if I don't make it to engineer, I can still be a tool maker, I can still be a high-level machinist. So I think math and science are really important, but there has to be practical applications as they grow up. We've moved away from that where kids are sitting in front of TV sets, they're not hands-on. We need to create hands-on generation of people. They really need to touch stuff.
Here where we have an industrial workstation that someone like a medical manufacturer or other industrial manufacturer would have on their manufacturing floor, and this would just be cutting tubes into small parts like stents or guide wires or other medical devices that can be cut from tubes. The laser that we manufacture here actually does it without heat, which is a big deal, particularly for these medical devices like the stents and scaffoldings that we were talking about earlier.
So we actually have several different disciplines that are represented. Optics and lasers is definitely a big part of what we do, but we also pull from different fields like electronics, electrical engineering, software engineering, both in terms of graphical types of software as well as embedded control systems. Then also mechanical engineering, because all of the optics and other components aren't going to float in free space. They need mechanics there to hold them and to hold alignment. So it's multiple disciplines and a lot of different skill sets.
What do we do? Triformix is an optics company, and we make lenses, basically. Not eyeglass lenses, but very specialized lenses, primarily for fiber optics. So there's kinds of three classes of things we do. A lot of fiber optic connectors. I'll describe what we have up on the projector here in a minute. We also make lenses for things like surgical cameras. So if you were going to have a knee surgery, orthoscopic, the surgeon goes in with a camera, and we make a little teeny lens that goes on the end of that camera. We're building those out back right now. And then we also make a number of specialized products for the military. Most all the lenses we make are used on lasers. And so there's a whole bunch of applications for military laser and interconnect applications.
Where is the next generation of these skills going to come from?
Well, I think the thing that we do is all about precision and building things. And so the first thing we really look for are people that want to build things. A lot of the work we do, as you can see out in the line, involves people really working with their hands with some really sophisticated machines. And I think the next generation is right around the table here. I really want to think you guys are the guys that we're going to hire next. If you get a chance to talk to Gene and the guys out in the shop, all of them came up through programs like you're in today. Most of them have gotten at a level where they're the best in the world. You have a shot of doing that. I'll tell you also, it's a great career path. They really do very well here. If you get an idea about how much money they make and what they get compensated, it's most of the machinists out here make more money than degreed engineers.